Hey, and welcome to assignment 4. In this assignment, we'll be focusing on how to configure the op-amps in Start and how we can simulate the AVR DB op-amp in MPLAB Mindi. The objective of this assignment is to understand how to configure the op-amps in Atmel Start, configure OP0 as a non-inverting PGA, plot the input and output of OP0 using the data visualizer, and simulate the non-inverting PGA. First, let's talk about the non-inverting PGA. It is a gain amplifier that does not invert your signal. What that means is that the output is equal to the input times some kind of positive factor. This factor is decided by the relationship between the two resistors R1 and R2. To achieve this configuration, you need to connect the negative input of the op-amp in between the resistors, and you have to connect the top of the resistor ladder to Vout and the bottom to ground. Let's take a look at this in simulation. Down below the video, you will find a link going to that simulation. If you press that link, you will get to this GitHub page, and all you need to do is to go to Releases, press Latest, and press on the source code, and you will download a zip. This zip you can extract, and inside it, you will find the schematic. As we can see, this schematic contains a model of the AVR DB op-amp configured as a non-inverting PGA. And we can see down in the table here the relationship between the gain of the PGA and the resistors R1 and R2. And we can also see which WIP position we need to configure the AVR DB to achieve this gain. So we want to have a gain of 2, therefore we want to set R1 and R2 to 32 kilo ohm. So let's write 32k here, and let's write 32k here. And if you now run the simulation, we will see that the output signal is twice as large as the input signal. So let's try and create this configuration in Atmel Start. Alright, so let's see how we configure this in Atmel Start. In the project, we'll press Reconfigure Atmel Start project to be able to look at how the op-amp driver is configured. This project is set up in the same way as it was for assignment 3, where the DAC is used to create a sin wave, which will be the input to the op-amp, and the ADC is used to measure the output of the op-amp. And both of these data points are streamed over USART to the data visualizer. So if you look at the op-amp driver, we will see that there is a basic driver, and we can select op-amp combinations. So for some of the more advanced op-amp configurations, multiple op-amps can be combined together. And here we can choose if we want one single op-amp and two op-amps connected, only single op-amps, or even triple op-amps. Not all configurations are available for all combinations of op-amp due to the restrictions of the multiplexers of each of the op-amps. If you want to look at which combinations of op-amp can create which configuration, you can have a look in the user guide, and you will see a table here for single op-amp, double and triple op-amp configurations. For this assignment, as OP1 can complete the non-inverting PGA on its own, we will use a single op-amp. If we go further down, we will see some global op-amp options, which affect all the operational amplifiers, and this is of course enabling the peripheral, and we can also set the input range, so we will have it to full range. This means that the op-amp will be rail to rail, but it will consume a bit more power. But if you are in the middle of the op-amp rails and you are concerned about power, you can also set it to reduced input range to save some power. Next, we'll see the op-amp configuration, and here you can enable and disable each of the op-amps. Next things that come up is that we can select which of the predefined configurations we want to use. So you have voltage follower, as we showed you in assignment 3. You have an inverting PGA, integrator, directly connected to pins, and custom. We want to use the non-inverting PGA. For every configuration, there is also an illustration showing how the operational amplifier is configured and how the output is related to the input. If we go further down, we'll see that there's a link here that will go to the GitHub repo that we just visited. And if we go down here, we'll see the individual op-amp settings. So here we can set what's going to be the input to the op-amp, and we want to use the DAC. And you can also set the resistor multiplexer Viper. So we know from the simulation that we want the two resistors to be equal, so we'll press this one. And we'll see down here that that gives us a gain of 2, exactly as we had in the simulation. All the fields that are grayed out are fields that we cannot change, because if we would change them, we would break the non-inverting PGA configuration. But they are still visible to us, so we can learn what kind of configurations are required to get the non-inverting PGA. If you scroll all the way at the bottom, we'll see some hardware settings. So, as in the previous example, the op-amp will be always on, and we'd have a normal output mode, as well as the settling time will be set to the maximum capacity. So let's flash the device and see how it looks in the data visualizer. As always, we have to load the workspace. Select assignment 4. We have to make sure that the COM port is set to 1152 0, 0, apply and play. We have to make sure that the decoder has the user as an input source. Then we can show live data. And here we can see that the output is twice as large as the input. Exactly as what we saw during the simulation. That's it for assignment 4. Thanks for watching.